what I want to start with is by just defining a few different types of formula. And the first one is an empirical formula. And an empirical formula is the lowest ratio, or the simplest whole number ratio of atoms. I think it's probably best if I give you the definitions and then look at a few examples. That gives us some information. It gives us information about what elements are present and their combining ratios. But it doesn't give us a huge amount of information. When we're dealing with covalent compounds, a much more useful formula is a molecular formula. And that tells us the actual numbers of each type of atom present. And a final definition, before giving you some examples, is a structural formula. And this is particularly applicable for molecules again. And the structural formula tells us the bonding arrangement. Well, I think this is probably easiest explained with a few examples, and I want to take those examples from the table on page 2 of topic 5. One can imagine a molecule such as hydrogen peroxide, which by chemical analysis we find has a 1-to-1 ratio of hydrogen and oxygen atoms. From what we know of the valence of oxygen, I know that can't be a stable arrangement, because I know that oxygen needs 2 bonds in a molecule in order to end up with 8 electrons around it. However, the empirical formula tells us what's present and the ratio of the atoms. The molecular formula for hydrogen peroxide, by further analysis, is H2O2. And now we're actually getting a lot more information. What this says is that each molecule of hydrogen peroxide contains 2 hydrogens and 2 oxygen atoms. The structural formula reveals the whole story. And shows you how those atoms are bonded together. And once we see that, we can understand that the valence of 1 for hydrogen, the valence of 2 for oxygen, and if we do the electron count, we'll find that that gives us completed electron shells for all those elements. Let me do another 2 examples. Water, of course, you're familiar with the formula. And this is a situation where the molecular formula is the same as the empirical formula. The structural formula, we're familiar with that. Oxygen as a central atom, flanked by 2 hydrogen atoms. And to give you one more example at this stage of a molecule that we had a look at yesterday, ethylene. It has an empirical formula of CH2, and once again our knowledge of valence and electron configuration tells us that can't be the whole story. The molecular formula C2H4 shows that each ethylene molecule contains 2 carbon atoms and 4 hydrogen atoms. And then the structural formula tells us how they're bonded together, and that in combination with our electron dot diagrams show us that we've got a double bond between the 2 carbon atoms, single bonds between carbon and hydrogen. Okay, well, for a molecule then, we use the molecular formula to provide the most amount of information. Something like methane, a formula of CH4, empirical formula and molecular formula is the same in that case. But what happens with an ionic compound? Well, this is my model of sodium chloride. And in an ionic compound, remember we have a vast array of cations and anions in 3 dimensions. As perhaps the name suggests, a molecular formula is not so appropriate for an ionic compound where we don't have molecules. What we do in ionic compounds is use an empirical formula by convention, i.e. the lowest whole number ratio of reacting species. So for sodium chloride, then it's just NaCl, but in the back of our minds we must remember that it's not small units of Na plus and Cl minus, but actually that's the common denominator of a crystal containing millions upon millions of ions of each sort. If I take another ionic compound, this one is, the mineral is called zinc blende, it's zinc sulfide, and there is a different ratio of zinc atoms, or there might be a different ratio of zinc atoms to sulfide atoms. It's not obvious in this case. I perhaps shouldn't have picked this one. This is a 1-to-1 ratio again, but a different look, different shape, because of the different sizes of the ions present. So, ionic materials, we always use an empirical formula, the lowest whole number ratio of the elements present. What about some other covalently bonded materials which we can't really consider as molecules? You're familiar with water, small molecule. I've mentioned that these compounds are often soft, volatile materials. Methane is a gas at room temperature. But then something like carbon, particularly the form of carbon that's diamond, we know is incredibly hard, incredibly high melting, a strong material. And this is a model of diamond where every carbon atom, indicated by the joints between the straws here, is bonded to 4 other carbon atoms. So we have not a discrete molecule, but we have a huge network of covalent bonds, and we call these network solids. In the case of carbon, we have 4 bonds to each carbon atom, as you'd expect. The total sum of all this bonding gives us a very rigid, strong material. How do I represent the formula? Well, once again, I represent the formula not in terms of the actual number of carbon atoms within this aggregate, because I don't know how many there are. It would depend on whether I've got a tiny speck or a lecture theatre sized diamond. We use the lowest ratio of atoms. Only one type of atom here, so I'd represent the formula of diamond as a simple C, simple carbon. If I look at one of the other allotropes of carbon, a quick reminder, an allotrope is different structural forms of a particular element. Carbon has diamond, it has graphite, which is a slightly different structure, a layer type structure. There are still actually 4 bonds associated with each carbon atom. This is one model of graphite. Different properties, but the common thing is that it's all made up of carbon atoms. We represent the formula for these network solids as the empirical formula, just C. If I look at a material like flint, silica, silicon dioxide, that is actually a large network solid, not dissimilar to that of diamond. And in that case, we use the empirical formula again, SiO2, to indicate the lowest ratio of atoms present. So molecular formulas are good for molecules. Empirical formulas we use for ionic compounds, we use for these network solids. And if I think about the elements of the periodic table, and I think for this I will go to the periodic table here. Now, I've mentioned that there are some elements which in nature always occur as diatomic molecules. And those elements include hydrogen. Let me put that over there. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, Astadine too, but I'm going to leave that out because it's rare, it's radioactive, it's not something we ever use. All those elements in the periodic table we signify as the molecular formula, H2, N2, O2, unless we specify otherwise. Of the elements, other elements in the periodic table, how do we specify them? Well, as it happens, the inert gases on the right-hand side, they actually do occur as single atoms in nature. Chlorine act with anything, even themselves, and so if we write Ar to represent an argon atom, that is actually a true representation because argon only occurs as single atoms. However, there's an awful lot of other things in the periodic table that occur as aggregates. We've seen a bonding model for metals, I showed you yesterday, where we have a structure of metal cations glued together by this sea of negative electrons. And once again, we, rather like ionic compounds, we use the empirical formula to represent the structure of all metals in nature as well as carbon. So the rest of the periodic table, we use the symbol of the element to indicate the empirical formula, but in the back of our mind we need to remember that actually they're not single atoms but aggregates of many millions of atoms. Okay, what I want to show you is a chemical reaction. This green stuff is actually just washing up detergent. What's more interesting is the gas. If I can get that a little bit more controlled. Oh, gas is lighter than air. And yes, you probably guessed it, it's hydrogen gas. This won't make a bang. No, this won't make a bang. I don't think. But what I want to do, well, it's currently showering me in the first two rows with soap. But it's quite nice. And of course, I told you it wouldn't make a bang. I have to believe everything I tell you. You get the orange flame, which is typical of hydrogen, the atomic emission spectrum of hydrogen. One more. Missed it. managed to put out the flame. Here we go. Okay, there we go. What I want to look at now is chemical equations. We've looked extensively at formulas. We can see there's nothing random about the formula of a compound. We can now predict the formula of any compound if I give you a couple of elements. Let's take this one stage further and look what happens when we actually form compounds, when we turn one compound into another. The driving force in almost all cases for chemical reactions is that we produce something more stable. There are also chemical reactions where we can supply sufficient energy that we can produce compounds which are less stable than the starting materials. They're slightly more difficult to do, slightly more unusual, but nevertheless we can do it. How do we represent a chemical equation? And let's look at the reaction that we've just demonstrated. I could write out an equation: hydrogen plus oxygen gives water, but that clearly takes quite a long time and is rather cumbersome. Better than that, I could give the chemical symbols of the materials involved. And with elements, we know that all elements are given there just a single symbol, the empirical formula, with the exception of those that form diatomic molecules naturally. So for hydrogen, we need to write it as H2. For oxygen, as O2. For the product water, we determine the formula by analysis as H2O. If I want to balance a chemical equation, I need to ensure that there are the same types of atoms on both sides of the arrow. And our convention is the arrow indicates reactants on the left, products on the right. So we need the same type of atoms on each side of the arrow, and we also need the same number of each type of atom on each side of the arrow. So this is an unbalanced chemical equation. Hydrogen looks good, there's two hydrogens on each side, but oxygen is unbalanced. How do we balance them? Well, it's a cyclic process, an iterative process. This is a fairly straightforward one to balance. The way I would do it is say, okay, oxygen is wrong, we need to fix that up. And I could fix it up by putting a half here, and that arithmetically would get everything looking good. Half of O2 would effectively be a single oxygen, and would have a single oxygen there. My preference, however, is not to use fractions when writing chemical equations. So it is better expressed in terms of two lots of H2O will now be balanced for oxygen atoms. It is unfortunately now unbalanced for hydrogen atoms, because I've got 4 hydrogens on the right, only 2 on the left, but I can fix that up by putting a 2 there as well. And I think it actually makes sense, more sense, to have whole number multipliers than to have fractional multipliers. You know, what is, on a molecular level, half an oxygen molecule? We don't know. Quick reminder of the convention: if there is a number in front of a formula, that means a multiplier of all that formula. So double, in this case, H2. We can go one stage further and indicate a little bit more information on this in terms of what we call the state symbols. The state of an element is whether it's a solid or a liquid or a gas, and in this case I know that hydrogen and oxygen are gases. There's a bit of energy given out in this reaction. We saw the light, there's a bit of heat too. Probably water was given out as a gas, but maybe a bit of experimentation would indicate Water is given out as a liquid, and we can use L to indicate that sort of situation. Very unlikely, of course, that we'll get ice cubes out of this reaction, but you never know. So another example, we can take, for example, the reaction of hydrogen and chlorine to give hydrogen chloride, H2 and Cl2 giving HCl, and all these are gases. The equation as such is unbalanced because I've got fewer atoms on the right-hand side than on the left-hand side. We need to obey the law of mass balance. We don't ever create or destroy matter, we just rearrange those atoms. The best way to balance that is with a 2 in front of the HCl. And let me do another rather more complicated example. C6H12O6 is glucose. It's a sugar. This is a molecular formula. Glucose is a molecule. The empirical formula for that would be the lowest ratio of atoms. And if I divide all those by 6, I get CH2O. So the empirical formula gives us some information. However, it turns out there's an awful lot of types of sugar, whether it be glucose or mannose or fructose, that have the same empirical formula, but there is some difference in their structure and possibly their molecular formula. You can see why sugar is part of a group of chemicals called carbohydrates, because it is, in the empirical formula sense, just carbon and water. Glucose itself has units, has molecules, 6 carbons, 12 hydrogens, 6 oxygens. And glucose is an energy source. It combines with oxygen to provide carbon dioxide, water, and in this case energy. And in terms of how we use carbohydrates, we use them as an energy source. We're not too interested in the byproducts of the reaction, or the products of the reaction, carbon dioxide and water. If I was to balance this equation, the way I would do it was say, okay, oxygen's going to be complicated because it occurs in all places. Hydrogen occurs just in one of the product molecules, one of the reactant molecules, similarly carbon. So they're two things that I will focus on first. And how about I take the heaviest of the elements of those two elements, in this case carbon, to look at first. 6 carbons on the left-hand side, therefore I need 6 carbons on the right-hand side. Now, I'm going to tackle hydrogen next because that occurs only once on both sides. 12 hydrogens on the left. I'm going to multiply water by 6, and that way I get 6 times 2, or 12 hydrogens on the right-hand side. Now it becomes a problem. I've got to fix up the oxygen. Let's see what we've got on the right. 6 times 2 is 12, plus 6 times 1. That gives us a total of 18 oxygens on the right. I've got 6 oxygens there, so I need, in order to balance that up, I need another 12 oxygens on the left. They come as O2 units. So 6 lots of O2 is 12 plus 6 gives me 18, and that means that that balances the 12 plus 6 on the right-hand side. So I've balanced up the equation. There really is no substitute for writing down a trial equation, trying it, see whether you balance some things. Sometimes when you balance one type of atom, you unbalance another type. Do it on paper, rather than in your head. I find that's much easier personally. I might include the state symbols here. Glucose is a solid, oxygen is a gas, carbon dioxide is a gas, and let's assume that we breathe out water vapor as the byproduct there. Okay, so that's a typical equation for a molecular situation, a reaction where we have covalent compounds reacting with one another, one molecule reacting with one another. What about the situation where we have the production of an ionic compound? Let's look at, say, sodium chloride. Well, the way I go about this is write down the elements, write down the formula of the product, and I know with ionic materials we use the empirical formula. I write the elements down in their conventional way. Sodium is just the empirical formula, but I know a chunk of sodium has millions of Na atoms. Chlorine, however, is one of the diatomic molecules, so we represent it as Cl2, not as Cl atoms. Balancing this up, I would have 2 lots of chlorine on the right now. I've created 2 Na atoms there. I need 2 Na atoms there. If I was to put in the state symbols, I happen to know that sodium's a solid, chlorine's a gas, sodium chloride is a solid. And as one final example, let's look at the reaction of, say, carbon as a non-metal with oxygen as a molecule, giving carbon dioxide as another molecule. Once again, I use the representation of the formula of the element as the empirical formula for carbon, and this looks like it's done itself. There's no further balancing to do. Okay, so to summarize what we've looked at in this lecture, we've looked at types of formula. We've found that there's empirical formula, and they're used extensively to represent ionic compounds and most of the elements of the periodic table. They're not so useful when we deal with molecules. For that case, we use a molecular formula where we actually indicate the number of atoms of each type present within the molecule. If we happen to have a giant network type compound where we have a 3-dimensional array of covalent bonds, such as something like silicon dioxide, then we're back to the empirical formula. But there are many, many molecules. Organic chemistry is molecular in nature, and of the 15 million compounds we have characterized in literature, 14.5 million are organic molecules. In that case, the molecular formula is not so useful. It doesn't give enough information. We might have to resort to a structural formula which indicates the arrangement of bonding within a molecule. And we'll see once we get into first year chem that there are many instances where the same molecular formula can lead to a number of different structures. In writing chemical equations, we need to balance from the left-hand side or the reactant side to the right-hand side the types of atoms present. And we need to balance the number of each type. The way we do this is a cyclic process, and there's no real substitute for trial and error. If you get to a stage where you have 41 molecules of X reacting with 27 of Y to give 322 of product Z, and it's still not balanced, I'd suggest you start again because you might have missed something. In general, we find that the numbers we need are relatively small in order to balance up the equations. Okay, have a break and then on to topic 5 tutorial.